The experiment which we are going to perform today is to plot the frequency response curve of a common emitter BJT RC coupled amplifier and to determine its input and output impedance. So basically we have to plot the frequency response curve. That means we have to see how a common emitter BJT RC coupled amplifier is responding with respect to the frequency and to determine its input and output impedances. So the apparatus we need is the power supply. So power supply, this is which is inbuilt in the box, and the second thing is AC millivolt meter. AC millivolt meter is, let's see, this is my true RMS AC millivolt meter. Okay, this has a range of 20 millivolt, 200 millivolt, 2 volt and 20 volt. So this is my AC millivolt meter. Then this is audio frequency oscillator and resistance box. Resistance box you already know is this thing, and the audio frequency oscillator we are using a function generator which will give us the frequency of generator, and we have to use the sine wave frequency, not the square wave of the sawtooth wave. So we are going to use only the sine wave generator, and the frequency of this sine wave we can change from this range and using this knob, and this knob is to change the amplitude of the sine wave function. Okay, so this is our audio frequency generator, basically which is a function generator which can generate a function of sine and square wave. In this experiment we use a sine wave function generator, and these are the range of the frequency which we can change using this knob, and using this knob we can change the amplitude of a function. Okay, so this experiment is for a single stage RC coupled amplifier. The box is for a study of a transistor amplifier which is RC coupled cum feedback amplifier. So this is a two-stage RC coupled amplifier, but we have to concentrate only this part for the single stage, in which we are going to have the capacitance and then these two resistance, and they are connected with a transistor, NPN transistor. These are the two resistance, one capacitor and this capacitor, and at this stage I am going to take the output. So this is a single stage. This part is a single stage RC coupled common emitter amplifier, and if I use this transistor also, then this will be two-stage with certain feedback. So now we are not interested in that. We are going to only use the single stage RC coupled common emitter amplifier. So the circuit is you can see is the same thing, is capacitor, two resistance is there, and two resistance, one NPN transistor and two resistance, output resistance in this. Okay, so the final circuit will look like this, that we have an input and input capacitor, and R1 R2 there are two resistance, RC RE, this is resistance with the collector and with the emitter, and then collector, this is going to the RC coupled common emitter configuration, single stage RC coupled amplifier in common emitter configuration, and there we are going to get the output, and plus CC and biasing voltage, plus CC and minus CC, which is all these are grounded. Fine. So this is a circuit diagram. Now based on this, let's see the observation table. How it looks like is in the first observation table is for the frequency response curve. So here you can see we have to change the frequency, and we have to note the output voltage. Okay, so the input we are going to give sine wave, we are going to change the frequency of this sine wave, and we have to note the output at this place. So note down the frequency, note down the output voltage, and then calculate the gain, which is output voltage upon V input. The V input, which we are going to make it constant, which is equal to 10 millivolt constant. So the input voltage we are going to give, the amplitude or the V input is going to be constant, which has to be 10 millivolt, but we have to change the frequency. Okay, so the input voltage will always be 10 millivolt, but we are going to change the frequency, and then correspondingly we have to see the output response of the single stage RC coupled amplifier in common emitter configuration. Okay, so how to perform the experiment is to first we have to fix the input of the input, which has to be 10 millivolt. And to do this, you can see that this is because this is our function generator through which we have to give the input, and this is the output wire through which we can supply a sine wave of certain frequency and certain amplitude. And this is our AC millivolt meter through which we are going to get the output voltage. Okay, so this input, this two terminal which we will supply here, which will act as an input, and the output part, this is my output part, this is my input part, and this is from where we have to take the output. So output part will be from the AC millivolt meter output, plus to plus and minus to negative to negative. Then we can take the output. So first thing is to fix the input voltage. So how to fix the input voltage? What we will do is we will take the two terminals of this function generator and the two terminal of the AC millivolt meter. Okay, so we will connect them together. We will connect the output these together. Okay, so how to connect it? Let's see it. So we will join positive to positive. Let me join it first. We'll join positive to positive, and then negative to negative. So these two wires, the output of the function generator and the output of the AC millivolt meter, I have joined them together. Now let's first choose the sine wave part, not the square wave, sine wave, and put the frequency. Let the frequency sorry, it is 42.97 point, make it 100. So with this knob I can change. You see it's changing. To let's make it first. Let's make it 100. So I'll start with 100. So you can see this is 100. Okay. Now we have to fix the input to 10 millivolt. So to read the 10 millivolt, I am fixing the knob at 20 millivolt. Okay, because here I can read the 10 millivolt situation. Now you can see this knob will change the amplitude, whether it has to be 5 millivolt or 10 millivolt or 2 millivolt. So if I vary this knob, so the output in the AC millivolt meter has to be 10 millivolt, because this is 20 millivolt range. So let us change this and try to fix the output to be 10 millivolt. Okay, now you can see this is fluctuating. It always fluctuates. So now it's around 10 millivolt. Okay, so this we have to keep fixed. Okay, now once I fix the input voltage, which I told you that it has to be 10 millivolt fixed. So this is 10 millivolt fixed by. So now what I am supplying is a sine wave with the amplitude of 10 millivolt. So now let's detach them to, and now this I am going to, because this is now supplying us a wave, sine wave of frequency of 100 hertz, and input amplitude is 10 millivolt. Okay, So now let's join it positive to positive and negative to negative. Now we have to see the output. Output we have to see again from the AC millivolt meter. So the output of the AC millivolt meter wire, and then we have to join positive to positive and negative to negative. Now you see what's the output here. So because it's out of the range, so I'm changing the range. Okay, you can see. Fine. Now you can see the output. It's coming out to be 0.438 or 6. It's slightly fluctuating volt because this is the knob is at 2 volt range, so it is 0.438 volts. So for 101.1 hertz of frequency and the input is fixed, which is 10 millivolt, so the output is 0.443441. So what we have to note down is, for like, because I have fixed 100 hertz of frequency, okay, so we have to note down the voltage output, which is 0.442, and then correspondingly we have to find the gain because V input is fixed, so this is 10 millivolt or okay, so then we have to find the gain. Similarly, we have to change the frequency from 100 to 200 and 500. Now let us keeping fix everything. Let us make it 200 hertz by changing this knob. You can see. Let us make it 200, and then the corresponding output is 0.698. So similarly we have to note for 200 hertz at 9.699, and the same way keep on increasing, like for 2000, like for 2000 let us choose the scale to 2 kilohertz and then make it 2000. So this is 2000, 2 kilohertz. Okay, for 2000 the output is 1.00, yeah, 0.999, whatever it is. Okay, so I could note down for 2000 has to be 0.999, and similarly keep on increasing. If I keep on increasing, the output will remain constant. If I make it like more, like make it 20,000, it's 927, and then if I increase, this is again, it becomes 962, and similarly keep on increasing, and then finally what will happen, it will decrease to 0. Okay, so if I keep on increasing or decreasing, and the corresponding frequency, we have to note it down. So then if I note down all the observations, response of the frequencies, and if I plot, because we see that if I plot it, like if I keep on increasing the frequency and calculating the gain, so what you can see that as I keep on increasing the frequency, the gain increases, and for a certain frequency range it remains constant, and then if I further keep on increasing the frequency, the gain drops down. So this will be the nature of the frequency response for this single stage RC coupled amplifier in common emitter configuration. Okay, so what we have to do is we have to note down the frequency and to output and the gain, and we have to plot it like this. On the x-axis the frequency, and on the y-axis the gain of the circuit, and if you plot it, it will come out to be like this. So then after doing this, what we have to do is we have to this is the maximum range, flat region of the gain. This is a maximum, and then we have to multiply it by 0.707, and then the value where you get the value of the gain, you draw a line here, and the line where the line cuts this lower frequency range and the higher frequency range, you have to come down to the frequency scale, and this f2 minus f1 will give you the bandwidth. Okay, so the F2 is the upper cutoff frequency and F1 is the lower cutoff frequency, upper cutoff frequency and the lower cutoff frequency, and this difference F2 minus F1 is called the bandwidth of the amplifier. Okay, so by multiplying the maximum gain of the circuit to reducing to 70%, and then where it cuts off the upper frequency range and the lower frequency range, and the difference will give you the bandwidth of the circuit. The first part of this experiment consists of this much, that we have to take change the frequency, calculate the gain, plot it, and calculate the bandwidth of the single stage RC coupled amplifier in common emitter configuration. For the second part of the experiment, what we have to do is basically this is for determination of the input impedance Z1. So we have to make the circuit is already there, and what we have to do is adjust input voltage to 10 millivolt as we have earlier done it, and set the frequency at 5 kilohertz. We have to set the frequency 5 kilohertz because why 5 kilohertz? The frequency you have to choose is the mid frequency. Whatever you plot the frequency and the gain in from the first observation, and then you have to plot it and then choose the mid frequency range, and whatever the frequency mid frequency range comes here, and then I have to fix that to find out the input impedance or the output impedance. So the input voltage we have to fix as we did earlier has to be 10 millivolt, and to have to set the frequency, the mid frequency range. Let us suppose right now it's 5 kilohertz. Okay, then what we have to do is like, as I have already fixed this to 5 kilohertz because the range is for 20 kilohertz, so I have make it 5 kilohertz, fix the frequency, and to the input V input, because I've already connected it, the output of this and output of this, to set the frequency, and then I have to fix the frequency input to 10 millivolt. Okay, let's fix it to 10 millivolt. You can see. Just make it 10 millivolt. 10. Okay, this is now the input is 10 millivolt and the frequency is fixed to the mid frequency range, and for now I have fixed it to 5 kilohertz. Now we have to do this. Now I am going to detach this, and then the input I am going to in input I have you can see here in input circuit I have to attach the resistance box in a series. So the ground is these are my two input. So the ground, this black one, is directly going to the circuit, and using this, the output, this will go to the resistance box, and from the resistance box it will come to the circuit. So this is like this. This is my resistance box. I have the two input of this resistance box. Okay, so this black one from the function generator is directly going into the circuit, and this is going to the one end of the resistance box. You can see this is going to the one end of the resistance box, and the other end of the resistance box is going to the circuits. So this is how I have connected the resistance box in series. Now after connecting this, I have to see the output of the circuit. So make it like positive to positive and negative to negative, and now we go to the output, changing the range. Let's see. Now you can see the output is 0.990. The next part is we have to choose the suitable resistance from the resistance box, so that the output, which is 995, become half of this. So I think it has to be 5.5. I have choose this 20,000. It becomes 522, and then more 200. It becomes 484. Okay. So now, for 20 and 2500 of omega, the output which was earlier 0.999, it becomes half of the outputs. So this the resistance for which the output of the circuit becomes half, at 5 kilohertz of frequency is my input impedance. Similarly, for output impedance, I have to keep the input voltage same, 10 millivolt, and the frequency same. But what we need to change is, in spite of connecting the resistance box in series in the input, I have to put the resistance box in parallel in the output. And then whatever the output was there, choose the right amount of the resistance from the resistance box so that the output becomes half of the earlier output. So these are the table into which you can see for the input impedance when we have connected the resistance box in the series. So keeping input voltage 10 millivolt and the frequency 5 kilohertz, whatever the output voltage, we have to choose this input impedance from the resistance box so that this output becomes half. Similarly, for the output impedance, where now we have to connect the resistance box in parallel in the output, keeping 10 volt, frequency 5 kilohertz, basically which is the mid frequency of the constant region, we have to choose the Z0 from the resistance box so that the output becomes half. So this is input impedance and this is for output impedance. So this is all about this experiment for single stage RC coupled common emitter amplifier. The frequency response curve is like this, and using that to circuit, keeping the resistance box in series as well as parallel in the output, we have to determine its input and output impedance, and from the frequency response curve we have to find the bandwidth of the corresponding circuit. That's all.